Good evening, everyone. I hope I am audible. And can you see my screen? Please write in the chat box. Okay, I have kept your microphones turned off. So if you can see my screen and can hear me, please just confirm. Okay. All right. Still coming in. Right. Hello, everyone. Good evening. My name is Saptarshi De. I am a PhD scholar at IITB. I am working on machine design, and in this semester, I will be working with Siva and Sai to take your doubt clearing classes for this NPTEL course on electric machines 1. This is the first class of the first week. There is one week zero video also. I don't know whether you have got the link where I have cleared some fundamentals. So there were several videos released in the NPTEL website. So those who have watched all of them, could you raise hands? I just want to see how many of you have already watched the videos. I can see Rahul. There is one raise hand option. Okay, those who have watched some videos, they also can raise your hands. Not all. Even if you have watched some, they also can raise your hands. Okay, around 7, I can say, maybe 10, let us say. All right, lower your hands, please. So, if you let us set up some rules that when you are not talking, you have to keep your microphones off. Okay. So, if you keep your microphones on, what happens is if your fan is running or someone is talking, that noise comes in that disturbs everyone. So, with that condition, I can allow you to turn on your microphone as it takes a lot of time to write in the chat. So, one by one, okay. When you talk, you will talk one by one. So, in this session, I mostly plan to solve some of the sample assignment questions. Not the exact assignment question, but some sample assignment questions which you can expect in your quizzes and exams. So you cannot turn on your microphone. But before going into those questions, I want to know from you whether you have some general doubt from the lectures or something else you wish to ask me.
Yes, sir, Rahul here.
Hi, Rahul.
Yes, sir, basically the phasor diagram. So, it's a bit of confusion about the phasor diagram.
All right, I want to know about phasor diagram.
Yes.
Rahul, which institute are you studying in?
Sorry.
Which institute are you studying in?
So actually, I am a graduate from 2020,
Okay.
and now I'm just preparing myself for further.
Okay. Okay.
Yeah.
So let us see. So what happens is, suppose I have, pardon my drawing. Okay, I am using not a tablet. So I have a transformer like this. Okay, and I am supplying a pure sinusoidal voltage to the transformer. Now, this sinusoidal voltage will push a sinusoidal current in this core, in this winding, and as a result, a sinusoidal flux will flow. Okay, so the flux that will flow, that we can write as phi equals some peak value phi max into sine omega t. Right. Now Faraday's law says that E equals d psi dt. Psi and phi are different. Psi is flux linkage. Okay. Phi is flux and psi is flux linkage. So d psi dt, flux linkage is nothing but number of turns time flux, d and d phi dt. So when I am writing n dphi dt now, if I substitute this with phi max sine omega t, what I am getting is essentially n phi max omega cos omega t. Okay. Now we know that we can write cos theta as sine 90 degree plus theta, right? So our flux was some phi m sine omega t, while our em voltage here, this actually this emf is this e, induced emf in this coil. This emf is equal to certain, say, I am writing this as capital E. So E cos omega t, or in other words that I have just written, sine 90 degree plus theta. And the supply voltage, if I write V and if I apply KVL here, I simply have V equals E, right? I simply have V equals E. So our V is also this. So what I get is my voltage will lead my flux by 90 degrees. So if I have flux in this direction, so let us write this as E1, I will have E1 in this direction, okay, and they will be 90 degree from each other. Now, if I have a secondary winding like this, where I have E2, and it depends on how you keep the dot convention. If you keep the dot convention like this, then your E2 is also here. Whether their relative magnitude will depend on the number of turns, the turns ratio. This is like this. Now, if you have a load here, say some lagging load, this load will draw a lagging current. Okay, so this current, say I2, will be somewhere here, I2. This is the load power factor, and this will be again reflected here as I1. So in primary we have two currents, I1 plus IM, magnetizing current. So where is your doubt? Okay, anyone else can go on? Anyone else has any other doubt? If not, then we will proceed to solving the assignment problems. All right, looks like all the doubts are cleared.
One more question, sir.
Yeah, go on.
Yes, sir. Sir, as you can see that here we pass the sinusoidal signal. So can we pass one square wave signal or something else? Yeah, only we have to pass the sinusoidal signal or DC signal.
The question that you have asked whether we can give square wave to a transformer, it has actually, that answer can be given from many perspectives. But to be very precise, you have learned about this equation that V1 by N1 equals V2 by N2. There can be others also. Now you have written this V in capital always, right? But remember that you can write them in small letter also. Or in other words, this V1 by N1 equals V2 by N2. This equation is not valid for RMS only. These are valid for instantaneous values. Okay. These equations are valid for instantaneous values. So if you have a square wave, sorry, I think just a minute. So if you have a square wave supplied to the primary of a transformer, in the secondary also you will get a square wave which is scaled up or scaled down, or maybe if it is an 1:1 transformer, similarly you will get a square wave also in the secondary. But why I said that there are several aspects of this question is that, see, a transformer primary is necessarily an inductor. Okay, so this is the magnetizing inductance that I'm drawing. You will learn about the equivalent circuit. So say this is the magnetizing inductance that I'm drawing in the transformer. So we know that voltage across an inductor V is given by L di dt. So if you do this di equals V dt 1 by L V dt, what you will get is when you give, so you have I equals V by L times T. So you have a ramp of current. So when you have a constant voltage in an inductor, the current increases in a straight line like this. So in this case, what will happen is the transformer current will look like this. So if I draw in this fashion, if I draw like this, then the current will be something like this. If you can make sure that your frequency of this square wave is such that the current the current value is not such that it crosses the flux limit of the core. There is no flux limit in per se, but from the saturation point of view. And also, if this RMS current is not crossing the RMS capability of the windings, then yes, perfectly, let's see, you can apply a square wave voltage in a transformer. In fact, if you study about power electronics in later stage, you will see that all the transformers are subjected to square wave voltage. Almost all the DC-DC converters in DC-DC, sorry, almost all the transformers in DC-DC converters, they are subjected to square wave voltage.
Yes, so I'd say one more thing, sir.
Yeah.
So, sir, basically, as you see that there is some DC transformer, right? So, what is the working principle of the DC transformer? As you see that, sir, in AC there is inductor works in AC, but it's have no response. It's at not that much response in DC. Then how it is work in DC transformer?
All right. So you are asking something about DC transformer. So
Exactly, sir.
my guess is you got this term DC transformer from power electronics only.
Yes, sir.
I cannot mention. Yeah. There is nothing called DC transformer. Even in power electronics, if there is a DC, actually the term DC transformer is wrong. If someone has told you or if you have read or heard it somewhere, that is wrong. But I am telling you why this misnomer might have come. What happens is in an isolated DC-DC converter, you have a transformer where the input is some DC voltage, let us say 10 volt, and output is some DC voltage, let us say 20 volt. These are DC voltages. But in there is a transformer in this circuit. So the confusion might have come from here that these are DC transformers working in DC, but no, these are not DC transformers. They are not working in DC. If you look at the transformer voltage, you will see like this transformer I can represent as an ideal transformer with magnetizing inductance in parallel. So if you look at the voltage here, you will see you will have square wave voltage. The voltage can be like this, the voltage can be a continuous something, but it is always a square wave voltage. This is not a DC transformer. What will happen is, suppose, let us say I have some transformer here, okay, and I apply really a DC. So we have V equals IR plus L di dt. Okay. This L is nothing but the magnetizing inductance. Let us say the secondary is open. I have just put a voltmeter here. So keeping a voltmeter is same as keeping it open. Now, if we solve this, we know that at steady state, we get I equals V by R. Now, what happens is in such case when we have inductor or transformer, the windings have very, very low resistance. And definitely this current will, will cross the rated value of the transformer. And if you manage to give a very, very low DC voltage, then what will happen is the primary current will increase like this, and in the secondary, when this primary current is increasing, then you will get a voltage which will then drop. It is like this. A transformer is transformer. Wherever you might use, it is high frequency or power frequency, the analysis and everything are the same. That does not change.
Okay, sir. So what if, sir, if I give DC supply instead of AC, whether the transformer is working or not?
I just told you that if you manage to give, then it will be like this, but you will not gain anything out of it. You will not get any continuous flow of power if you supply DC.
Is there any damage through the transformer if I?
Yes, definitely there will be. If your voltage is large enough so that this current I equals V by R is above the RMS current rating of the windings, then it will get damaged.
Thank you, sir.
Any other doubt? My ink is visible, right, to you?
Yes, sir.
Okay. Any more doubt?
So I know this is a failure doubt, but
No, go on.
yeah. So basically, we know that the transformer rating is kVA instead of or another. So why so, sir? So because of everybody have some different way to explain it. So can you please explain that so that it's get more clarity to me?
Okay. So why is transformer rated in kVA? Let us look at it from the design point of view. Okay. Design point of view, we will try to answer. So if we see here kVA, right? So we have two terms here, voltage and current. Okay. Now an engineer is designing a transformer, so he or she is designing the windings for the same. Now while the windings are being designed, there are two things to think about. Number of turn is one thing, but from this volt and current, if I look at, first thing is what is the cross section area of this conductor? Why is this important? Because this is the current density, okay, current flowing per unit cross section area. This has certain value. Say transformers are oil cooled, that is oil cooled, you can go to as high value as 12 ampere per millimeter squared or something like that. 10 to 12, that can be done. If I exceed this value, or if the transformer is designed in such a fashion that at rated load current, this current density value is exceeding, what will happen is there will be so much I squared R loss in the windings, then the cooling system won't be able to dissipate it or remove away the heat from the winding fast. As a result, the winding will burn down. Right, so the winding, whenever you are making a transformer, you are taking a certain gauge of where your winding, your current rating is fixed. Certain RMS value, beyond that you cannot push. Second thing is the insulation. Insulation, two insulations are mostly there. Firstly, winding, so this is one turn, this is another turn, so there must be some insulation. This insulation must be able to defend the turn-to-turn voltage. There is a voltage per turn, it must be able to withstand. And secondly, the insulation between the winding and the core. Okay, so this should be able to, this if the core is grounded, then this should be able, this insulation should be able to uh, withstand that much of voltage, the rated voltage. Okay, so as soon as you have given certain insulation to the transformer, your voltage rating is fixed. So once a transformer is designed and manufactured, the voltage and current ratings of the transformers are fixed. Okay, now suppose I rate this current as 100 watt. Let us say I rate this current as 100 watt. So what I do is, there is a AC source here, and I am putting a load which is a pure inductor, right? Or maybe a pure capacitor, right? So what is the energy that this source is, or what is the power, not energy, what is the power that this source is transferring? Zero. Because this inductor or capacitor, they do not draw any real power. But there is current flowing through the windings. There is current flowing through the windings. If you put an inductor very low value, such that this current is so high that it crosses the RMS rating, the winding will burn down. Now you will come to me and complain that you said that 100 watt, but I put an inductor which is 0 watt. How would the transformer burn down? That is why wattage is not the factor. Although you are drawing 0 watt, maybe you are drawing 150 volt ampere reactive. You were drawing maybe 150 volt ampere reactive. Now this requires some current. The current was not 0. And the winding does not understand whether there is active power or not. It only understands I square or loss. Winding will burn down. Similarly, if you put high voltage, even if the secondary is open, if the voltage is say 2 times, 3 times the rated, the insulation will fail. That is why this voltage and current figures are necessary. That is why transformers are rated in kVA. Wattage. Hey, who is this guy? See, this platform is not for any kind of informal conversation, okay? Alright, I hope I could make your doubt clear.
Yes, sir.
Alright. Anyone has any other doubt?
Sir, excuse me.
Yeah.
Sir, if we apply a low frequency or higher frequency signal that is sinusoidal to transformer, it's working the same or it's change?
Alright, so no frequency is DC, right? DC, I have
No frequency means that's DC. That's you already explained, sir. If the frequency value is very high, or I say that's 5 hertz or 10 hertz.
That is low. 5 hertz 10 hertz is low frequency, very low frequency.
Yeah, sir.
Okay, so you mute yourself. I will explain. So in the very beginning, I showed you this thing that if my flux again, this thickness, I will increase. What is happening? Okay. I'm still not conversant with this. All right. So I have shown that if your flux is given by some phi m sine omega t, your EMF will be given by n phi m omega cos omega t. This E is nothing but the V. V is the supply voltage to the transformer. Okay, this is E, this is V. Right, so this is the peak value of the flux. Now this voltage is also sinusoidal. Say if my voltage is this, then my current, then my flux will be this. Okay. So let us now talk about the peak value. Okay, the peak value of voltage Vmax, that will be equal to. So Vmax is V is nothing but this cos omega t. So this is Vmax. That is n phi m omega. What is omega? Omega is 2 pi f. 2 pi n phi max into frequency. This is a line frequency. Now suppose you have a transformer which is designed for 230 volt and 50 hertz, and you connect that transformer to a supply of 230 volt, say 60 hertz. If you go to US, or maybe if you go to Japan, you will see the 60 hertz supply. The voltage will be lesser though, 110 volt, but let us take an example of 230 volt, 60 hertz. What will happen? Let us see. So this is VM. Okay. Now, I have not changed the voltage, so my VM is fixed. This equation has to hold good everywhere. My VM is fixed. 2 pi is a constant. N is the number of turns that is fixed. So what I have is, I have this frequency times peak flux as a constant. It's a K. Now in my, what I have done is, I have connected the transformer to a I have connected the transformer to a supply of higher frequency. So its flux flowing through it will reduce. So the core will be underutilized. On the other hand, if you connect it to a supply of very low frequency, the flux will increase a lot. And it might happen that what happens is, when we are designing the core, so this is the BH curve of the material that we are using to design the core, not this much, where is it, this much. We make sure that the perturbation is here, that is, the flux is varying in this zone. Now if you connect it to a very low frequency, your B will increase. You will come and operate here. As a result, what will happen is your magnetizing reactance will drop at that high frequency. This is called saturation. In this region, your magnetizing inductance will drop. The transformer will draw a large no-load current. The no-load current itself will be very large. So you might not be able to supply the full load. Might not be able to connect a full load to the transformer. Not only that, this also creates distortion in the no-load current. Not only no-load current, the transformer current, it creates a distortion, this kind of situation.
Sir, what effect on the losses of transformer?
Losses on transformer, there are losses like winding losses is not affected. Let us say the load, you have limited the load such a fashion that your winding current is not exceeding the rated RMS current. So ohmic loss is not changed. So there are two kind of loss. One is ohmic loss, other is core loss. Now core loss has two components. One is hysteresis loss, other is eddy current loss. Now with increasing values of B and F, these hysteresis and eddy current losses will increase. I do not remember the exact expression for them. You can look about it. That is Steinmetz equation. This talks about the loss calculation, core loss calculation, and both the losses, that is core loss PC, that is a function of, say, f to the power f raised to some power b raised to some power. As far as I can recall, eddy current is proportional to f squared and hysteresis is proportional
That's
to
FD square, sir. That is FD square.
FD squared. Which one is that? Is it eddy or hysteresis?
Yeah, that's eddy current.
FD squared and hysteresis is between 1.6.
Yeah, 1.6. D to the power 1.6.
This 1.6 is called the Steinmetz constant.
Yeah, 1 minus x, that's the Steinmetz factor.
So, this is f square, is it? Okay, anyway, please check it, okay? You will very easily get it. Just search for Steinmetz equation. I forgot the exact expressions. So what your question was, what will happen to the loss? If you increase the frequency, the core loss will increase. Reducing
Yes,
the
sir.
frequency, reduce the core loss.
Pardon, sir?
If you increase the frequency, your core losses will increase.
Okay, sir.
both kind of losses, AD and hysteresis loss.
In case of we will increase the frequency or
Yes.
decrease.
Increase. You see, both of them are raised to powers here. If I make frequency twice, AD loss will be twice.
Okay.
It will increase.
And if we reduce the frequency, the losses are reduced.
If you reduce the frequency, core loss will reduce, but there are like I took an assumption at the very beginning that I am not exceeding the current beyond the RMS value. But if you simply look at the no load condition, at a reduced frequency, your core loss will reduce, but your ohmic loss will increase. It will draw more current, as I told.
But sir, at that time the transformer is working saturation actually.
That depends on the frequency. But generally, what people do is they design the transformer at this knee point so that the core is maximally utilized. So chances are, yes, if you reduce the frequency by what you said, 5-10 hertz, it will definitely go into saturation.
Thank you, sir.
Generally, in power system, we do not see a frequency below 48 hertz.
Yeah, exactly, sir. But I just tell on the behalf of gate. That's why.
Sure. Okay, any more doubt? Okay, since you talked about core loss and frequency, let me tell you one more thing that might not be very much relevant here. The thing is, the DC transformer that someone was talking about, forgot his name, those DC transformer, the materials used there are not as the power transformer materials. The power transformer materials that the power transformer transformers that you see, or the distribution transformers that you see, they are very low frequency transformer, 50 hertz transformers. Okay. As a result, their flux, they're low frequency. So the material that is used there is a kind of electrical steel, like M235 can be one option, M19, these kind of steels are used. But if you go to very high frequency, like the DC transformer, I should not say that again, high frequency transformer, we would say, okay, high frequency transformer, they are such a high frequency, say 10 kilohertz. In this high frequency area, power electronics area, 10 kilohertz is a very low frequency, okay. High frequency people are nowadays working in hundreds of kilohertz or maybe even more. Here the core loss is so high with this kind of electrical steel that they cannot be used here. What we use there, there might be some advanced materials also nowadays, but conventionally what is used is ferrite, powdered ferrite. So iron is powdered like this and they are pressed together. They are insulated obviously and pressed together. As a result, eddy current cannot flow in between them. Lamination does not work there. You have to powder them and press them together so that the eddy current is very, very less. This is done to reduce the core loss in very high frequency transformers that work in tens or hundreds of kilohertz frequency. But don't be confused, the theory of transformer is the same. That does not change. Any more doubt? Okay. You can always interrupt me if you have any doubt, but since we have half an hour left, I will try to solve some problems, some sample problems that I got. Okay. So we have already discussed this, right? What did we get? We got that, we got that E equals N into 5x. Just in the last page I derived this. I'm not writing this from memory. Into, if you have doubt, you can ask. N phi omega cos omega t. This thing I wrote, any doubt about it, you can ask me. Again, I have shown that this V is equal to E, right? The question is that a transformer coil with 250 turns is connected to a 60 Hz 400 volt RMS supply. Estimate the peak value of the flux in milliweber. Okay. So just the way we write that V equals V max cos omega t. This expression is nothing but this. So this is my V max. This is my V max. V max is N phi max into omega. Omega is again 2 pi f. So n phi max. So from here, can you find phi max? Is simply v by 2 pi f n. Okay. You need some more assistance with this problem.
No, sir.
A simple, straightforward problem. We'll look into this. This is an interesting problem. So see here, we have three coils in a transformer. I have a power supply in one, and I have load in the other two. So how to analyze these kind of transformers where you have a large, where you have many windings? Okay. Okay. So suppose I take a loop like this, and it has an anticlockwise sense of rotation. If I integrate the magnetizing force H dot dl, line integration of this magnetizing force over a closed loop, what do I get? I get MMF. MMF is Ni. Right? MMF is Ni. This Ni is the total amount of current enclosed inside this loop. Now, how to know what is the total amount of current enclosed in this loop? See, I have taken this in an anti-clockwise fashion. So, if you curl your hands like this, any current that is coming out of the plane will be considered a positive current, and any current that is going inside the plane will be considered a negative current, right? So inside the loop, you see all the currents in this primary, they are going inside, and all the currents, they are coming outside. Again, I am telling you, see, these are nothing but conventions. Even if you don't draw it like them, what will happen? Simply the magnitude of current will reverse. It does not matter. What matters is once you have drawn the windings and once you have drawn the loop, then you have to stick to your convention. So what I have is, from here, I can write that minus N1 I1 plus N2 I2 plus N3 I3 equals 0. Why 0? Because I took this closed loop. Okay, I took this closed loop, and in a transformer, it does not matter whether you are operating it at no load, operating it at full load, the flux in the core does not change in an ideal transformer. If you are not connecting any load, the flux flowing to the core is the rated flux. If you connect some load, there is more current in the primary, but there is current in the secondary too. So they are cancelling each other's flux. So again, the flux is constant, irrespective of whether you load the current or not. So whenever you have a transformer with multiple windings, you have to do this MMF balance. First, you make sure your conventions are okay, direction conventions. When you make them, stick to it. So according to our convention, what we have is MMF balance gives us N1 I1 equals N2 I2 plus N3 I3. Okay. Now we will look into the question. The question says, in the above figure, they have given the number of turns, they have given the load resistances R2, R3, and they have given the primary current, 9 ampere primary current is flowing. Okay. And we have to find out these quantities, RMS in I2, I3, primary voltage RMS, power delivered, and impedance seen by the source. Okay. Let us see how to do that. So we have, how many equations we have? We have this equation. Let us put values, whatever values we have in, and we will put. So I have 100 into 9 equals, into I2 is 125, into I2 I don't have, I have to find out, and N3 is 50 times I3. Clear. But in this equation, I have one equation, I have two unknowns, so I have to find another equation. So what is another equation? You see, this current is flowing in this resistance. So there is a voltage drop here. Let us call this as V2. Another voltage drop here, V3. Now, this V2 and V3, they are coupled to the same core. So their ratio must be the same as this turns ratio. So I have V2 by V3, which is I2 R2 by I3 R3 equal to N2 by N3. Let us put values. So I have R2 as 100, so 100 I2 by 75 I3 equals 125 by 50. So now I have two equations. I have equation 1 where I2, I3 are unknown, equation 2 where I2, I3 are unknown. Can you solve this and quickly tell me the values of I2 and I3? And also, if you have any doubt, you can ask. Are you
Sir,
solving?
by directly find out the turns ratio, N1 by N2 or N1 by N3,
Mhm.
and directly also I1 is given in the question. We directly 9 multiply by the turns ratio N1 by N2.
You are suggesting to use this equation?
Turns ratio. Yeah, sir.
See, this
That's what you said.
equation. Hmm? No,
ये
I am
काम
telling
करेगा
you.
सर?
I am telling you. See, this thing what we do is in our transformer lesson. So if I first find out that V1 by V2 equals N1 by N2, then we apply a power balance. We know that V1 I1 is equals V2 I2, and from there we come to this equation N1 I1 equals N2 I2, right? But if you look closely, see, this is nothing but the MMF balance equation of the transformer.
Sir,
When you have a transformer with two windings, then this is okay. Then this is nothing but the MMF balance equation that we just derived here. But now you have three sources of MMF, three sources of magnetic force. So N1 I1 equals N2 I2 plus something should come, isn't it?
yes, sir.
That is why you cannot use this equation here.
But
Because
sir, if in case the question I2 and I3 is given, then we transfer the I2 to I3 to I1. That is okay.
yes, that can be done. Suppose I2, I3 are given. Say I2, I3 given, and all the terms are given. Then you can simply apply this equation and get I1.
Okay.
So yeah, go on.
But we don't transform the I1 to the I2 to I3.
No, this okay. Let me generalize it for you. So if I have a transformer which has n number of windings, so the winding with ni number of turns is carrying a current I1, and similarly the winding with n, so winding N1 is carrying I1 and winding NN is carrying IN. In general, winding NI, that is NI number of turns, is carrying IY, II. Most importantly, all windings are wound in same sense. Okay. If so, then I can write summation over I equals 1 to N Ni II equals 0. So if you have 4, 5, 10, 11, 100 turns, this equation always holds good. We have a 3 winding transformer here. See, okay, let us see, we have three winding transformer here, but see, their sense of winding is different. For this winding, I am calling this winding 1, calling this winding 2, calling this winding 3. For the
Fine, sir.
winding
Understood, sir.
2 and 3, see, the sense is same. Winding 1, the sense is opposite.
Fine, sir. Fine.
Okay, could someone solve this equation? I have the answers with me. Just don't want to. Okay, make sure you solve this problem. Okay, do not just write down the answers. I am writing down the answers. I solved it, but do not write down the answers. Make sure that you solve this problem. I2 and I3 will be 5.9 and 3.2 amperes. I am writing down these figures because I have to calculate some other things also. Right. Now I have I2 and I3. These currents we know. RMS currents we have got by solving these equations. These two, if you solve these two simultaneous equations, the linear equations, you will get this. Now the question is RMS value of primary voltage. There are two ways to do. You find out the voltage V2, which is I2 R2, and then transform it by multiplying it with N1 by N2, or the other way around. You find out V3, I3 R3, and then multiply it with N1 by N3 and find out the RMS voltage of the primary. Okay. So the RMS voltage of the primary will be, I can write it as I2 R2, then, sorry, N1 by N2. Or I can write I3 R3 times N1 by N3. Why? How do I know that this voltage is RMS? This voltage is not peak or something else. That is because it is given 9 ampere. All the values are in RMS. So our 9 ampere RMS will, when drop across, when 9 ampere RMS when flows across a resistance, it will create an RMS voltage. 9 into 100, 900 volt RMS voltage. Dipanjan is asking, will we get recordings of this course? See, I am recording. I will upload it on YouTube, but I don't know whether this will be shared with you. Okay, at the end of the class, I will give you the link of my channel. You can see the recording there. Remind me, okay, if I forget. All right. So, any doubt in how to find out the RMS value of the primary voltage? Okay. So the next part is power delivered by the source. Now I want this answer from you. Anyone?
That is, sir, source voltage multiplied by current.
You are saying source voltage multiplied by current, but do you know about the power factor?
Sir, because there is a resistive load in both sides.
Yeah. So we can say, since this is an ideal transformer and the loads are purely resistive, you can do V1 simply multiply the RMS voltage and RMS current of the primary and get the input current. But there might be non-idealities also, like in the next week you will learn about non-ideal transformers. So in such a case, it is okay, you are fine. That is one way. V1 I1 plus 5. Another way that I was going to tell is, in this case, we can simply do is power delivered is I2 squared R2 plus I3 squared R3. In case of a real transformer, you have to add the losses also, so as to find out the power delivered by the source. In the next week, I think you will learn about non-ideal transformers.
Sir, if this is practical transformer, that equation is right for that also.
Which equation?
I2 square R2 plus I3 square R3 plus losses.
Yes, this is the most general equation. For any electrical apparatus, the input power is given by the output power plus losses.
Plus
That is true for any system, not only electric.
okay. No, that means in that case we don't need to bother about the power factor.
There are two ways of calculating it. One is this: if you have if you have load current, load resistance values with you, you can do. If you can calculate the losses separately, you can do in this way. Or if you have the whole, the whole circuit, equivalent circuit, you can find out all the currents. Now the magnitude will not do. You have to find out the currents with their angle. All the vector calculations you have to do the way you have done, and then find out the current in I angle theta. You get the voltage V. You have VI cos theta. That is also true. You should ideally get the same value.
Sure.
All right. So we have one more. Here, impedance seen by the source. Impedance seen by the source, there are two ways to do here. Now, I will ask you to verify this. I have not verified this. So if that is not true, tell me in the next class. What is the impedance seen by the source? Very simple. Voltage by current. You have VRMS, you have IRMS in the primary. In the primary side, you do VRMS by IRMS, you get the impedance. But let us try to think in some other way. So see, we have two loads, R2 and R3. Can I not transform them in this way? I have two loads that are carrying two separate voltage currents, but can I not transform both of them to primary and then find out how much is the equivalent impedance? Is it not possible? Can you please verify it and tell him in the next class? You got the problem, what I want you to verify?
Yeah, exactly.
You understood why I took them in parallel? Because basically, see, there are two loads in at your home when you are turning on the light and then turning on the fan. They are getting in parallel to each other. Here also, there are two loads. Both are getting power from here, so they are in parallel. Just verify it. It should be true. Okay. Any more doubts from this?
It shows I2 plus I3 is equals to I1.
No. When you have to do this, see, when you are transforming, your currents are also getting transforming, aren't they? Is the current I2 here? I have referred them to primary.
Yeah. That is the transformation current.
Yeah. It is I3 times N3 by N1.
By N1. Yes,
This is I1. Now is it matching?
Okay. Fine.
We could have done this also. We could have drawn this circuit, then analyze it. It would give the same results. Okay, any more doubt from this question? This is the question. All right. So if not, okay, so Shivananda asking, sir, can you please repeat why you take the MMF of primary winding as negative in MMF balance equation? See, whenever I am writing something in general, right, say here I wrote a general equation, summation over all the MMF equal to 0. I have to make all of them same. Right? I cannot say that I have 100 turns, 100 windings, the second one and the fourth one are different. That is not a generalized situation. So when I am writing this equation, I have taken that all of them are wound in the same sense. Same sense means, say, I take this is the positive port of all the winding, if a positive current flows from the positive port of all the of any winding, it will create a flux in the same direction in the core. That means the same sense. This means the same sense. Okay. Now here, if you see, if you have a current like this in this winding, you have a flux like this. Right? And if you have a current like this, you have a flux like this. They are wound in opposite direction, in opposite sense. Just imagine like this. Suppose you hold this winding with your hand and then drag it along this arm and bring it on the same arm. You see, they will look the opposite. Can you imagine? I will copy this and stick it here. This and paste it here. Imagine this winding. You are dragging with your hands and you are holding with your hand and dragging here. Once this winding is here, how will it look? See, this will come up to the top. So this will look the opposite. This will start from below. I don't have space to draw. Start from below and come opposite, like this. So this winding and this winding, they are in opposite sense. That's why. So if I follow the generalized equation and write, if I have a sense like this of the loop, Ampere's loop, then it will be, this one will become negative. Then only we can generalize. Unless you keep everyone on the same platform, you cannot generalize. Is it clear? Okay, Shivaram, I almost missed your message, so if people can unmute and talk, but make sure that once you are done, you unmute yourself. Sorry, mute yourself. This is a simple question. In the above figure, you have given primary voltage, transformer turns ratio, this impedance, and this load resistance. You have been asked to find out the RMS value of the primary current, secondary current, and power supplied by the source. How to do this? We have to take everyone on the same platform, on the same site.
So just to transfer the secondary resistance to the primary.
That's it. So if I transform the secondary resistance to the primary, this Jx does not change. This thing becomes N1 by N2 squared RL. Right? So what value of RL do I have? I have 4 times N1 by N2 is 2 squared. So 16. Right? So RL when transformed to primary is 16 ohm. And X is given 12 ohm. So what is the net impedance seen by them? Can someone say? It is 12 plus J. Sorry, not 12 plus J. 16 plus J 12. So what is the magnitude? I would be very happy if everyone talks one by one, obviously. Tell me what I have to do.
20 ohm.
How do we get it?
So by
12 plus the 16 square under root.
Sorry?
12 square plus 16 square under
12 square
root.
plus 16 square under root equal to 20. So you have 20 ohm. This will give you the current. Okay. You have 200 volt, you have 20 ohm, you have 10 ampere of RMS current. Right. What else? Okay. Some power, RMS value of the secondary current. Just transfer it. Secondary number of, see, do not always see to the formulae. Simply look at it. Secondary turns is half. Secondary voltage will be half. So its current will be double. So secondary current will be 2 times 20 ampere. Total is equal to the formula. Power supplied by the source. Go on. What do I have to do? Tell me what is the power.
Just multi-square, sir. I1 square into R2. Yes, sir.
Once more. Which I?
Sir, that is in primary side.
Primary I
10
squared times
into
resistance.
R2, which is referred to the secondary side.
Primary side.
Sorry, primary side.
RL prime. So basically I have my primary current was 20 squared times 16. Right?
Yes, sir.
Okay. We will try to look.
6400 rupees.
Sorry?
No, sir. Thank you.
Did I do anything wrong? Let me just check with my answers. No, sorry, I did something. Did some mistake. Did I make some mistake? Can you please check?
That's 10 ampere current, sir, actually. The current is I1 is 10 ampere.
10 ampere. Oh, sorry, the 20 was the secondary, right?
Yeah. Yes.
This is the primary, sorry. I took wrong value. I took wrong value. So primary current was 10 ampere. 10 squared times this 1600. Let us try to do it some other way. Okay, VI cos phi. Can you do it VI cos phi?
Yes, sir.
What do you have? You have 16J here. Sorry, 16J12 here. And
10 inverse of 16 by 12, sir.
2. So, tan inverse of 16 by 12. This will give you the power factor angle, phi.
Yes, sir.
So, all you have to do is VI cos phi.
Yes, sir.
They will come the same. You can verify this, okay? I have given you 2 things to verify. This will surely match, no doubt. Okay, one
Sir,
last.
ये questions मिल सकते हैं नहीं? Anyhow.
I have only these 4 questions that you are already getting. You will get the, what is that called? The recording also.
Okay.
This
Thank you so much,
I
sir.
have. This last question I think will be discussed by the other TAs are there, Siva and Sai. I am leaving. Let me just complete it. It will not take much time. Just a second. So this question, someone asked what will happen if I change the frequency of a transformer. See what happened here is that some 60 Hertz transformer was there and then it was used in 50 Hertz transformer. Okay, so what you do is you go to Japan, you pick up one transformer, you take it to India and there you're using in India. The question is, under this situation, what is the maximum amount of kVA that this transformer can handle so that the no-load current is not more than the rated no-load current? Okay. So let us try to understand the question first. Why would someone ask this? Why would the no-load current rated, this thing will be important here? Okay, let's try to understand that first. Problem then you can solve. We have seen this, that E equals N phi omega cos or sine, whatever you can write. This thing we have seen. So what have we seen? We have seen that phi max equals N phi max omega. Okay. Now, suppose when I take the transformer to India, I am connecting it to the same amount of supply voltage. So I have kept this fixed. N is the number of turns that I am not touching the transformer. My omega has dropped. So definitely flux will increase. Now try to understand the problem, what will happen. The same transformer I have connected to a lower frequency and I am seeing that the flux has increased. Now what is flux? We know that in any magnetic circuit, magnetomotive force MMF is given by the flux times the reluctance. Everyone knows this? And this MMF is nothing but Ni, number of turns into current. So I have not done anything to transform, I have just connected it to the 50 Hz supply and now it is experiencing flux more than the rated because the frequency is now a lower frequency than rated, so the flux is more than rated. So what is happening is, if this flux is more, and see, reluctance is a property of the magnetic circuit, so I don't know about it. It is not changing. It's the same. So this MMF must have increased. Now my number of turns I have not touched, so the current must have increased. So what happens when you take a transformer from Japan and connect it in India, even in no load, it will draw more current at the same voltage. At the same voltage, it will draw more current, right? The no load current itself is increasing because the frequency has reduced. Now look at the question. Now the question will make sense. Under this situation, what is the maximum amount of kVA that this transformer can handle so that the no load current is not more than the rated no load current? So my no load current has increased. The question is, I cannot let my no load current go beyond its rated value. So what is the option left to me? Can anyone answer? I have a transformer. I imported it from Japan. Japan people, why I am saying Japan is because they are the 60 Hz power system in Japan. So I took it to India and connected it to a 50 Hz supply. I have kept the voltage same. And I am seeing that I have not connected any load, but still it is drawing more current. The no load current has increased. Why? I have explained. Any doubt in the explanation? Okay. So no load current has increased. The question is, I cannot let the no load current increase. What I have to do? The only option left with me is reduce the voltage. In India, I cannot reduce the power frequency. It is 50 Hz fixed. So I have to reduce the voltage so that my no load current is equal to the rated no load current. The question is how much? The question is how much? This is very easy. Simply you write, see, what I said is that my no load current I am not changing. Means my rated MMF, hence my rated flux I am not changing. So Vm by N omega, V1 by N omega 1, this should be equal to, this is a constant because my phi I am keeping at rated, V2 by N omega 2. Any doubt about this? Till now tell me.
No, sir.
So V1 I have this. So what do I have? Let us say my V1 is Japan, okay? So I have V1 by V2 equals omega 1 by omega 2. Now I am taking ratio of frequencies. So when you are taking ratios of frequencies, does not matter whether you are taking hertz or radians per second. So Japan is 60, India is 50, 60 by 50. So my V1 by V2 will be 60 by 50. So my voltage has to be reduced. So my voltage in India V2 is 5 by 6 times V1. I cannot operate this transformer anymore in its rated voltage if I have to keep the no load current at rated. I have to reduce the voltage by this much of factor. So if my voltage is reduced by this much of factor and my current is kept constant, my KVA rating will also be reduced by this much of factor, isn't it? It was 24 initially. It becomes 5 into 4, 20 kVA. So this is the rating. I have to, I cannot exceed this much of volt ampere rating. You see, we are again coming back to that question, why is transformer rated at kVA? Just a minute, I cannot take this thing properly. Yeah. See, I had to reduce the voltage. Suppose had I not reduced the voltage, what would happen? Had I not reduced the voltage, my no load current would be more. And there would have been a ceiling, the rated current ceiling, where I would not be able to reach because the flux would be more than the rated. Alright, here I am keeping the flux constant, I am not changing the flux. So to make sure the flux is at its rated value, I told you that we cannot go beyond the rated value of flux to saturate, other problems will come in. Since I am keeping my flux at its rated value, so I have to reduce my voltage so that my no load current reduces and my flux is within the limit. That is why, since my voltage is reducing and my current is not reducing, my KVA rating is simply 5 by 6 times the KVA rating. I will get 20 KVA. This is the maximum I can operate with this transformer. Is it clear? We have already crossed our time. I will quickly give you.
Sir, last question, please.
Yeah, sure.
Sir, if registers that the insulation level which is mentioned, मतलब I want to say कि अगर उसका जो voltage है सर वो भी anyhow कोई ऐसा clause दे दे कि वो भी हम increase नहीं कर सकते, otherwise.
Shovik, I would request you to speak in English because there are people from all over India.
Okay, sorry sir. My question is, if we are unable to increase the voltage level,
Why would I try to increase the voltage level?
you mean to say, sir, in that case, okay, we reduce the, sorry, fine, sir. Cleared, sir.
Okay, so that's all for today. I will quickly give you the link to my YouTube channel. I will upload all the videos of our weekly session to this channel. How to copy this?
Oh, thank you so much.
Okay, so this is the channel. How can I share? In the meantime, if anyone, yeah, go on.
Sir, if we have any further doubts, how can we get to know, like, how we can ask?
I think you have already been communicated that there will be three doubt clearing sessions per week.
Okay, sir.
Those people you can ask. Siva and Sai will be there.
Okay, sir.
Probably Tuesday you have one. Siva will take on Tuesday.
So please share the link in the chat section, please.
Yes, that I'm trying. How to share? I'm trying. Just a minute. Okay, I'm sharing it here. Comment it. I will upload. Okay, I'm stopping the recording for today. It's done.